Hello.
Hi, hi everyone. A very warm welcome from Corentin and myself to the new episode of Astronomy on Tap London, as usual, stay at home edition. So brace yourself for a very mysterious topic today and be ready to start with us an investigation of extremely fascinating objects residing really far away from us when the universe was just a baby. So before introducing our guest, I would like to remind you that we'll have a Q&A session after the talk. So please post your questions in the YouTube chat. And also don't forget to subscribe to our YouTube channel and to follow us on our social media channels to keep up to date with the next events. So now I'll give the word to Corentin to present our speaker.
Yeah, hello and welcome everybody for this new episode of Astronomy on Tap, well, off tap. So tonight we have the pleasure of hosting Ricarda Beckmann. So Ricarda, you did your PhD at Oxford and then you moved to Paris at the Institute of Astrophysics for a postdoctorate where we actually met. And now you're moved back to the UK and you're based in Cambridge. Yeah, is that correct?
That's correct.
Could you before you start, could you tell us how you ended up like studying black holes?
How does one get into black holes? It was a little bit of an accidental sort of pathway. Like I find many things in life, especially this kind of thing, tend to come together a bit serendipitously. In my case, I ended up with this particular topic because I happened to be doing a summer internship during my final year during undergrad, which was in numerical material science, which sounds completely unrelated, but that's really how I got started with the computation and the simulations. And then topic-wise, I, for my master's thesis, worked on something called loop quantum cosmology, which was very, very theoretical. And I wanted to continue in that, but it turns out there wasn't a lot of projects in it. So while I was looking for a topic to work on, I ended up sort of combining the two and going into numerical galaxy evolution, and then found a great project that focused on black holes, and I've worked on black holes ever since, really.
Well, brilliant. It demonstrates that you don't have to like to be born with a telescope in the hands to actually do astrophysics. All right. Well, I guess I'll give you the screen, Ricarda. You can start sharing. Well, and the screen is yours, and so is the sound.
Thank you, Corentin. Right, welcome everybody. I want to today spend a little bit of time giving you an insight into the key question that I try to answer with my own work, and in particular try to point out, why we think there's a mystery there, and maybe a little glimpse on how we have started answering some of the questions surrounding it. As I said, as Corentin said, my name is Ricarda, and I'm a research fellow at the University of Cambridge at the moment. So before I get into the mysteries of the first supermassive black holes, I want to start more simply and go briefly through what a black hole is intuitively. And to do that, I need to take even a further step back and talk you through briefly through a concept called the escape velocity. Now, the escape velocity is is something you can calculate for every massive body in the universe. If you imagine you stood on Earth and you're holding a ball, if you throw the ball in the air, it will fly up some way and then it will come back down. But if you throw your ball harder, it will fly up higher before coming back down. Now, for each massive body in the universe, there's a velocity where if you could throw the ball at that velocity, the ball would fly clean off and fly so far, it'd leave the sort of gravitational field of the Earth, never to return. So it never reaches the point where it sort of turns around in its trajectory, and instead it just escapes out to space. That velocity that you'd need to throw your ball with is called the escape velocity. And what that velocity is for each object, whether it's the moon or the Earth or a whole galaxy, depends on two key variables. It depends on the total mass. So for a planet, it'll be the mass of the planet, and it depends on the size, because typically the escape velocity is calculated from the surface. So if an object is smaller for the same mass, you are closer to the object, the gravitational acceleration goes up, and so does your escape velocity. Conversely, if you're already out in space, say you're out in a rocket, your escape velocity is lower because you're further away from the distance of the object. So what does that have to do with black holes? Well, to give you a few little examples on how escape velocities shape. If anybody remembers the comet with the unpronounceable name that was visited by the Rosetta mission a few years ago, that is a very small object that's floating in space, but if you can imagine standing on the top and throwing your ball, you'd only have to throw it with about a meter a second, which is about 3.6 kilometers an hour, for it to escape forevermore. So if you threw a ball, like a human could easily do it. That's a small, very light object. The reason the speed is so low is mostly because it's very light. If you're on Earth, as in my example earlier, the escape speed is more like 11,000 meters a second, or conversely about 33,000 kilometers an hour, which is obviously incredibly fast, which is why we need huge rockets to try to get out into space. Now, what about a black hole? So where does that take us? Black holes are incredibly massive. They're both incredibly massive and incredibly small. Both contrive to the fact that they have very, very high escape velocities. In fact, a black hole by definition is an object that has an escape velocity faster than the speed of light. So faster than 300 million meters a second. How does that work? If you imagine you have a huge amount of mass in a very small volume, and you're near the surface of it, and you're trying to send out a ray of light. Now, light travels, by definition, at the speed of light. Nothing can travel faster than the speed of light, so that really is the upper limit that anything can move at. What happens is that if the speed of light of the light is less than the escape velocity of the object, it will turn around, the same way that a ball does. So what happens is that even the light cannot escape the object. It goes some way and it turns around. Now, if you go a little bit further away from the object, your escape velocity starts dropping, but there will still be a region where even there, light will be forced to turn around and fall back. But if you're sufficiently far away from the black hole, eventually you hit a point where the escape velocity drops low enough that the speed of light is it is smaller than the speed of light, and then light, traveling at the speed of light, can escape. This is what we call the event horizon, and anything within the event horizon is what we call a black hole. So a black hole is an object that is so massive and so compact that you can be close enough that this region exists where even light isn't fast enough to escape its gravitational attraction. Seen from the outside, what we would call the size of the black hole is the size of the event horizon, since we can only see light that escapes, and any light that's within that volume can never escape and is therefore, from our point of view, within the black hole. What sort of typical quantities do you have to have a black hole? Well, it depends wildly, but the objects we're going to be talking about today are supermassive black holes. Black holes can be as light as a few solar masses, so a few times the mass of the sun, and as massive as the supermassive objects I'm going to be talking about today. A supermassive black hole has the mass of a small galaxy. This is an image of a real galaxy taken with the Hubble Space Telescope. It's a dwarf galaxy called NGC 5477. And it weighs about 1 billion solar masses. So it has about 1 billion stars in it. You can see, in the image here, it's a sizable structured galaxy. And a supermassive black hole has the same mass as that galaxy, but in a much smaller volume. How small? Well, if that's, so roughly across our black hole, I've just cut it off a little bit for space purposes, then you'd have to squash the entire galaxy, the entire NGC 5477, into roughly the size of the solar system. So somewhere between the center of the sun and out to the orbit of Neptune, which feels like a big volume from our point of view, but is incredibly small on a cosmic scale, especially when compared to the size of a galaxy, which is many, many, many times larger than that. So to give you a feeling, if we wanted to turn the Earth into a black hole, we could do that. We'd have to compact it. As I said, lots of mass in small volumes is how you get a black hole. So if you took the Earth and squashed it down to about the size of a pea, we'd end up with a black hole. So that tells you how incredibly dense these objects are and how much mass they contain and how small a volume. So how does one make a massive black hole? How do you get so much mass into such an object? You start with a small black hole. That sounds a bit daft, but we have a very good understanding of how small black holes are formed. They're often left over when old stars die. It's one of the possible sort of remnants left at the end of a star's lifetime. And there's a few other ways in which you could potentially make small black holes, but there are several channels that produce them, and they typically sort of start out weighing maybe a few hundred times the mass of the sun. which is obviously a long way from the billion solar masses I just talked about for the supermassive black holes. So to grow it, there's two different channels how you can grow a black hole. Black holes have a clear relation between mass and size. So adding mass makes the black hole bigger. Generally, when we say grow, we talk about adding mass. So the way to grow them is two ways. One is that there's huge amounts of free gas in the universe. So that's gas that's not in the form of stars, but really is in the form of these huge clouds that are frequently found in galaxies. And a lot of that gas is thought to, it's flowing like a fluid, and it can be attracted by the gravitational potential of the black hole. It will fall in, cross the event horizon, and anything that crosses the event horizon never ever comes back out. So it becomes part of the black hole, and the black hole gains mass every time this gas sort of falls into it. The alternative is black hole collisions. This has been talked about a lot recently by the gravitational waves, since these are all based on black hole collisions. But fundamentally, if you take two black holes and they collide, they make a bigger black hole, since they sort of fuse into one bigger object. So both of these ways, and often a combination of them, is how you turn a smaller black hole or a lighter black hole into a bigger, heavier black hole. So that sounds like it's easy, but as I said, we need an awful lot of gas. And I wanted to particularly talk a little bit about the gas accretion, because that's the way we think that particularly the first supermassive black holes, which is what I work on, tend to grow. So what I've got here is an image of a galaxy from a simulation. This is not an observation. This was done with a computer. It's a project I've been involved with called the Near Horizon simulation. And what we see here is we see the gas density. Right, so there's a lot of free gas in galaxies. So these are not the stars. This is the gas that hasn't been bound to stars yet. And generally, the brighter and yellower, the more gas there is. So what we have is we have a lot of sort of diffuser, reddish gas, and then we have all these very, very dense clumps. And a galaxy like this, in many cases, has a supermassive black hole in the center. So the supermassive black holes are found at the center of galaxies. I've drawn it on here because really it's so small you would never be able to see it in an image. So think of this more as a sort of location pointer than the actual black hole. But black holes are found in the center of galaxies. And that means they're sort of right in the center of all this gas supply of the galaxy. And the gas can then flow, through the sort of spiral structure of the galaxy as the galaxy rotates around it, become closer and closer to the black hole, and eventually cross the event horizon and be accreted. The problem is that this process, while very efficient in some ways, takes an awful lot of time, because often the distances to be crossed are absolutely vast. And there's all sorts of processes that can disrupt the gas flows. So this is in general, while very efficient, and it also can take a very, very long time. And there's also another limiting factor which makes it hard to grow black holes fast. There's something we call self-regulation built into the process. If you have a black hole that is surrounded by a bunch of clouds of gas that are falling onto the black hole, what ends up happening is that as the gas approaches the black hole and gets very close nearby, it gets very, very hot and starts emitting a lot of photons, a lot of light, very energetic light. This light, in turn, because it's outside the black hole, this is to do with gas that hasn't quite fallen in yet, but it's got quite close, will be radiating outwards and encounter the clouds that are falling inwards. So from the point of view of the clouds, this light acts a little bit like a headwind. So it sort of pushes the clouds that are trying to fall into the black hole back, making it much harder for them to keep falling in. The faster the black hole is growing, the more of this light is emitted, and the more the pushback is, which means that in a sense, the black hole sort of cuts off its own gas supply, because eventually the clouds are unable to continue falling onto the black hole, and the sort of growth of the black hole stops. We call this a self-regulating process, since it's sort of directly coupled. How much falls in, this is how much energy comes out, is how much the process gets slowed down. But in practice, it means that there's a maximum possible growth rate for black holes via this gas accretion process. And it's very hard to exceed it because of this inherent mechanism where the black hole regulates its own growth over time. The other problem to do with why it is very hard to make supermassive black holes is that the range of mass scales to be crossed is absolutely massive. Newly formed black holes are very light. As I said, there's a few different ways of making them, but none of them produces a black hole that's bigger than 10,000 solar masses. That sounds a lot, but if you compare the number of zeros to the number of zeros in the mass of an actual supermassive black hole, a billion, you can notice that we need an awful lot of extra zeros, which means that the black hole needs to keep multiplying its own weight again and again and again to go from where we know they are formed to where we finally observed them with telescopes. It's a little bit like trying to grow the mass of a sesame seed to about the mass of a smart car to give you a feeling for how many orders of magnitude is between them. So that means that the black hole, even after being born, needs to assemble an absolutely vast amount of gas to become as big as we know they are, because that's how big we see them. So where does this fall into the sort of larger picture of how the universe evolves over time? I've put together a little timeline of the universe for you here. Generally, if you start with the Big Bang, and then the universe has been evolving for about 13 billion years to where we are today. Now, where do sort of black holes form and where do we see them? The very first small black holes, what we call seed black holes, form very early. They form when the universe was less than 1 billion years old. And that gives them plenty of time to grow across cosmic time to become the incredibly massive objects we see in galaxies near us today. So from this point of view, this matches very well with what we understand about black hole growth. It fits in with this image of limited growth. It fits in with what we know about how often black holes collide. There's plenty of times for black holes to grow to the massive objects we see today. But there's a problem with this picture, and that is the fact that we not only see black holes today that are as massive as these supermassive objects are, we see them much earlier. We see them when the universe was only 7 billion years old. We see them when the universe was only 5 billion years old. And we even already see supermassive black holes that are as big as the biggest supermassive black holes we see today when the universe was only 1 billion years old. And this is where it gets tricky. This is where our understanding of how black holes grow is being challenged significantly. There's 3 key insights to take away from this image. The first one is different black holes grow at very different rates. Some black holes seem to take all 13 billion years to go from the original size to the billion solar masses we see them at. Others, on the other hand, seem to take a lot less, maybe just a few billion years. So clearly, black hole growth for different black holes occurs at different speeds. The second point to notice that the early black holes that were already so massive early in the universe then don't continue growing. So you could say, okay, some are just growing very fast and they just continue growing, but then today they would be significantly more massive than the billion solar masses we see them at. So clearly, black hole growth eventually cuts itself off and stops. It's not a runaway process that continues, but rather black holes seem to grow to sort of a maximum mass roughly and then tend to roughly stay there. And then there's the question that I'm particularly concerned with how is it possible that the very first black holes managed to grow so massive in such a limited time? Because the first black holes must have grown extremely quickly. There's only a very small space where they could have, grown. Since the universe simply wasn't any older, there's no extra time to be had. So they must have grown very, very quickly during that space. How quickly? I'd say unlikely quickly, but not impossibly. So when it comes to our understanding of how black holes grow, it is possible for the black holes to grow this fast, but it's extremely unlikely, especially given what we know about the early universe. So that then raises all sorts of interesting questions. Is there something we fundamentally misunderstood about how black holes grow? Is there something we've not really understood yet? Is there maybe something special about the early universe that allows them to grow a lot faster than it grows across the rest of cosmic time? Or maybe is there something that creates the special conditions that are possibly necessary for these black holes to grow so efficiently and reach these masses that we observe in the time span that is available to them? And again, is it something about their host galaxies maybe? Is it something about the environment in which they are? What is it that allows these black holes to grow so quickly? And that's the question I work on in my own research. Answering it would take many more talks, and there's in fact many unanswered questions, but I just wanted to spend a few more minutes giving you a little glimpse of what the early universe looks like and why this is such a fascinating piece of cosmic history to be investigating. So at the top, I still got the same timeline I had before, but at the bottom here, I've done like a little blown out timeline. So we go from the Big Bang at the left all the way to 1 billion years at the end, which is when we see the first supermassive black holes. This is a time when a lot was happening in the universe. We are used to the universe looking a certain way. Around us, we have massive galaxies full of stars, many old stars that aren't very active anymore. We tend to have supermassive black holes in the centers, and everything is sort of, well, there's evolution in general already quite settled. That was not true in the early universe. It was not only the time when the first supermassive black holes first emerged, it was also the time when everything else first emerged. The Big Bang was the beginning, there was nothing then there. And after sort of the early sort of formation of atoms and molecules and such, the universe became filled with this fairly distribution of gas, which then later collapsed to form the first stars, for example. The first small black holes formed that might later grow into the first supermassive black holes. Then more stars formed, the first galaxies started emerging. So before them, we can't really talk about having galaxies in the same way. There was a time known as reionization when gas in the universe went from neutral to ionized, which was a very violent process that involved a lot of sort of stir of energy exchange. So in general, the early universe was a time when not only black holes were forming, but when a huge amount was going on. It was a very messy time, which makes it both interesting and challenging to understand how black holes could have grown in this particular time. I want to spend a little bit of time showing you a movie of one of the simulations colleagues of mine and I used to study the early universe and in fact galaxy evolution across different cosmic times as well. So what I'm going to show you is something called the New Horizons simulation, and you're going to see lots of little proto-galaxies collapsing, combining, and you're going to see how the gas evolves in the early universe. So if I start this off, we see the first sort of dense objects forming. Each of these little points is a little proto-galaxies full of early stars. And you can see it was a very violent time in the universe. We have huge explosions, gas is flowing, it's colliding, things are collapsing and being destroyed again. And only now are we beginning to form objects that are big enough that we can start thinking of them really as galaxies in the traditional sense. And during this time, it was somewhere in these early galaxies, in these proto-galaxies, in these converging gas flows, and within all these explosions and energy emissions that are taking place here, that the first supermassive black holes must have somehow found access to enough gas to grow from their seed masses all the way to the supermassive. They must have done that impossible jump from the sesame seed to the smart car in the limited period of time that was available. So that really, for me, is the mystery of the universe. Are the little black holes there? How are they finding enough gas to keep growing and grow to the masses where we are? What is it particularly about the early universe that's allowing them to do this, which is then a process that seems to slow down later throughout the rest of cosmic history? And I think I've used up my time, so I will leave this here. Thank you.
Thank you very much, Ricarda. It was a lovely presentation. And thank you for this journey across time and very close to supermassive black holes. So we have already a few questions in the chat. Maybe I'll start with the first one. So what about the escape velocity? So what is the direction of the escape velocity? Is like this straight up from the main mass, or to escape an object we need to take a different path?
So the escape velocity is generally measured straight up. You can go at an angle as well, but then you have to go even faster, because what matters is how fast you are moving away from the surface that you're trying to escape from. So if you're spending a lot of your energy going across, then you're going to have to go even faster to make up for it.
Okay, so Corentin, can you go with the second one? Also, Ricarda, if you can stop sharing so we can go back to the panel view. Thank you.
Definitely.
We have another question by Chung Myung Mu. So the question is again about escape velocity. So the question is, well, if you start accelerating, for example, on Earth, if you accelerate a rocket, you can leave without reaching the escape velocity. Is that something that is correct? And why by accelerating you couldn't escape black hole?
So so that is correct. So the way a rocket works is, in the image I was talking about, a ball only gains velocity in the beginning, and from that point onwards it only starts losing it. So as it falls, it's very fast in the beginning, then it's slow until it basically stops, and then it turns around and falls back down. A rocket doesn't quite work like that, right? A rocket is going to keep accelerating you, so it's going to keep pushing and pushing So if you're in a rocket, you never reach the escape velocity, but you still spend the energy that would have been needed to move you to the escape velocity to counteract the gravitational pull. The reason that doesn't work is because for a black hole is because the amount of energy that would be needed becomes huge. You know, it's always a big amount of energy we can already see. We need to burn a lot of fuel to get off Earth, but for a black hole, that's going to literally infinity. So it becomes impossible to put enough energy in to keep accelerating yourself against the pull of the black hole. And you know, mathematically it works out, but the sort of intuitive idea is you could never put enough fuel in your rocket to do it.
Thank you, Ricardo. And then the other question is, would a black hole grow by accreting dark matter?
Yes, in principle, yes. Anything that goes in a black hole is a way to grow a black hole. For example, there's people thinking about what happens to stars specifically. I only really talked about gas. I have to add though that the dark matter falling into black holes is a topic that isn't very well understood. Mostly because there is dark matter in galaxies, but there's actually a lot more gas and stars. So we tend to focus on the gas and stars since there's just so much more of them available that if you're trying to think about the mass growth, the dark matter is probably comparatively unimportant. That's the logic. That being said, you know, yes, in principle, and I think it's, you know, I'm sure it's something somebody's working on somewhere.
So if we extend that, we can also imagine having like stars like getting disrupted by black holes and stuff like that.
Definitely. That's called the tidal disruption event when that happens. So stars, if you have two black holes, you do have the two black holes and they just tend to, they don't head on collide, they spiral round and round and round and round and round until they both end up in the center and they collide. It's not quite what happens if you have a star getting too close to a black hole, because the difference between the black hole and the star is that a star is much bigger and it's like a compact cloud of gas, basically. So as it gets nearby, the black hole is so strong, it starts tearing the star apart. So the star sort of gets shredded, basically, and becomes like a long sort of ring of gas, which then eventually falls back down into the black hole. So it's not a head-on collision, it's more a sort of disruption event, which is why we call them tidal disruption events.
That doesn't sound like a good way to end a star. Another question from the chat is whether growing supermassive black holes is easier in the early universe because there's more mass or energy and things are denser.
So yes, to some extent. So in general, there's a trend that, especially if you look at very long cosmic timescales, if you're very late, for example, today, there is free gas, but actually a lot of the free gas is already in stars. And once it's in stars, it's much harder to access for the black hole for various reasons. So in the sense, yes, it's easier to grow black holes in the early universe because there is a lot more free gas around. So from that point of view, it's much easier to access that. There are other things that make it harder to grow black holes in the early universe, though. For example, the fact that there's a lot of newly born stars which tend to explode very violently. You saw that in the movie. There were these big sort of reddish bubbles appearing, and that is young stars living very fast and dying very violently, and they tend to blow a lot of the gas away. So while there is a lot of gas around, it's very hard to keep the gas in galaxies and near the black hole. And if it's not, and black holes are very small in the cosmic, you know, they're massive, but they're not very big in space. So you need to get the gas very close to the black hole for it to be accreted, and which is very hard in the early universe.
Thank you, Ricardo. And also people are appreciating your diagrams. And indeed, I have to say that written slides are really nice. Well done. Okay, so I think we have no more questions from the chat. So, well, thanks a lot for your talk. It was a really great presentation and very fascinating topic. So thank you very much, Ricarda.
Thank you for having me.
Bye, everyone.
Bye.
Okay, I've